So everyone, welcome to another First Friday VSA Oberlin Acoustics Workshop online seminar. Today we're happy to have Professor Jim Woodhouse again, and he's going to be talking about wolf notes. Jim?
Hi everyone. Yes, again he's right, it's Fan's fault. I think he had a gap in his program, so he said, couldn't you give this talk again? So let me put up my, hang on. I'll put up my title slide for a moment, but then I'll turn it off in a second. So this is, as it says, a talk, or a slightly tweaked version of a talk I gave at Oberlin, or remotely to Oberlin in 2018. I got the slides out and didn't quite like what I'd done then, so I've tweaked it a little, but the content is the same. But that's too bad. It's Fan's fault. If you're going to say you've heard all this before, that's absolutely fine. I just put a plug for my web project that I'm doing at the moment. I haven't got to wolf notes yet in euphonics.org, but I will get there. But there's all kinds of other stuff. And I'm really interested in feedback. Anyone wants to browse through those and tell me to explain things better, or why didn't I mention something, I would be really pleased to hear from you. Okay, but now I'm just going to stop sharing for a moment. I thought that although all these violin makers, you will kind of know what a wolf is, but you probably have a different attitude to it from us scientists, because you will perceive wolf notes as simply a problem, so you only want to hear it enough to say we need to get rid of that. And maybe you don't take time to tease out the wonderful warbling behavior, which I will be talking about. So with a bit of luck, I may just be able to, my cello has a classic wolf here, and I should be able to demonstrate that on if it's a good day. And then later in the talk, I'll explain what's happening. But just in case you've never really thought about what the warbling sound is like, I've marked the place so I can do this. So is that warbling coming through all right? Somebody nod. Try to do it again. That's not my shaky bow hand, that's the string is choosing to do that under the bow. It's a bow control exercise to get it to do it really steadily. So that's the phenomenon that I'm going to be talking about. I think players in particular may describe anything they don't like as a wolf, but that's your classic warbling wolf. So let me find the share button again, and yes, and slides, and do it. So here's something else you've probably all seen before, but you need to have this anchored in your mind. Helmholtzs Motion. This is with an exaggerated scale here, and this red animation line. This is what your string of your violin or your cello is doing when you're doing what you normally want to do. Now, players sometimes want to make all kinds of funny noises, but this is what your violin teacher wants you to be doing with your string. Now, here's Helmholtz. Helmholtz observed this way back in the 1870s. Absolutely astonishing experiment for those days, because that's before electronics was developed, and he had to do it by mechanical experiment. So here's your bow, and you can see it moving because I've got knots in the bow here moving along with it. Here's your string, and it's got this corner which is shuttling backwards and forth between the bridge and your finger. Now watch what the string is doing under the bow. All the time the corner is traveling out to your finger and back, the string is attached to one of these knots and it's sticking to the bow. The corner then hits the bow, unsticks it, and while the corner is whizzing around the short distance of the bridge and back, the strings against the bow hair are sliding backwards. So it's a stick, slip, vibration, mostly sticking, one slip per cycle. Now, synchronized down here, this is the waveform of force that's applied to the bridge. So this is the force that's driving the instrument body, violin or cello, whatever it may be. And that force in the perpendicular direction, parallel to the bridge top, and that force is simply governed by the tension of the string and this angle between the string and the bridge. So the string simply pulls in the way it's facing. So you get this sawtooth wave. You watch the angle at the bridge, it's increasing, increasing, increasing until the corner zaps on the bridge, and then it jumps down. Then it increases, increases. So remember this sawtooth waveform, you're going to see a real version in a moment. So that's what Helmholtz motion should look like if you measure this waveform at the bridge. Now, here we're going to want to understand Shellings diagram. Don't panic if you don't already know this. I'm going to talk you through this in gory detail. But this is a famous diagram done by John Schelling in the 1970s, I think, 73, something like that, which encapsulates in a diagram something that all string players know. Now, it's got kind of three regions. There's this triangular region of this diagram. I'll explain what the diagram is in a moment, which says Helmholtz motion. And outside that, there are bad things going on that I'll talk about at the moment. Now, what are the axes? Well, the player, if you're just talking about steady notes, I was talking about transients last time, no transients today. If you're playing a steady note, then the player controls three things, four if you include bow tilt, which I'm not going to talk about. So you control the speed of the bow, you control the force, which players have a bad habit of calling pressure, and you control the position of the on the string, whether you're near the bridge, near the fingerboard. Well, we can't draw pictures in 3 dimensions. So Schelling decided to say, suppose we've already decided the bow speed, then we've got the bow position on the string and the bow force. And that's what this diagram is. So some point in this plane is saying I'm playing a certain distance from the bridge and I'm pressing with a certain down force, but I'm always going at 10 centimeters a second or whatever I'm doing. In that diagram, and I'm not going to go through the theory of this, but you can only get the thing you want, which is this Helmholtz motion, in this funny triangular region. We'll talk more about that in a moment. If you go outside that region, something goes wrong. Now, that's no surprise to players. You choose a fixed position and a fixed bow speed. You get it doing the right thing, then you press harder and harder and harder, and something will go wrong, won't it? The force gets too high, and let's do it. So, Helmholtz motion, I press too hard, and I might get some kind of horrible crunch noise like that. So that's the thing that says raucous. And that's caused by the string carrying on sticking to the bow hair when Helmholtz's corner comes round. It doesn't let go when you want it to. The opposite extreme is if you don't press hard enough, and that's when your violin teacher tells you off for not getting into the string or surface sound or whatever. So instead of all those sort of sul ponticello noises, and that's when the opposite problem occurs and the string slips too soon. It doesn't carry on sticking all the time you want it to. So, well, that was me saying something happens. Let's just look at some measurements. Is that really what happens? So here's a violin bridge that I've built some little force sensors. So under each string notch, there's something that measures the transverse force, that thing that should be the sawtooth waveform for the Helmholtz motion. So armed with something like that, here are some typical measured waveforms from a real string. So here's Helmholtz's motion, looking more or less like the sawtooth that we saw in the idealized animation. Got some little wiggles, there's a story there, but basically it does do what Helmholtz said it should do. Here's an example. There is no typical example here, but an example of the horrible crunch noise when you press too hard. It's no longer a regular waveform. It's doing all kinds of random stuff, different random stuff every time you do it. So there is no typical raucous motion, but it's just, we've lost the nice timekeeping from that corner rattling up and down on the string, and it just doesn't know what to do. Here's a typical example of surface sound. If you slip a little bit too low in your force, you might get this sort of waveform. Now, this is still more or less a regular repeating waveform, and you can see what it's doing. It's a kind of double sawtooth. It's got a big jump and a little jump in it. The string is slipping on the bow hairs twice in every cycle, or could be 3 times or 4 times, depending all those different noises you can make as you do sul ponticello stuff. So that's what's going on. So we understand more or less what it was. Schelling understood more or less. Well, this understanding goes right back to Raman in the early years of the 20th century. Over 100 years ago now, people have kind of understood this. Right, the thing that Schelling put together was this diagram where he focused on what's the boundary line, what limits the range where you can get Helmholtz motion. So we got a maximum force and a minimum force, and he did a bit of theory, and I'm not going to go through any theory here. I'm just going to tell you the important thing, which is that both of those force limits, and I'm not telling you anything here that you didn't already know, both of them depend on where you choose to put your bow on the string. As you move closer to the bridge, you have to press harder, and you have a narrower range. That's what this triangular region is saying. Your maximum force line goes up as you get nearer to the bridge, which is this direction. Your minimum force line also goes up, and it goes up more quickly. And so they might actually meet somewhere. So if you're, does this all make sense? As you move closer to the bridge, you have to press harder, and you also have to, you're constrained to a tighter interval where things can work and where things will go wrong if you do it wrong. So that's why beginners stick down here, because it's safe. Now, what's all this got to do with wolf notes? We'll come to that in a moment. The next question we're going to ask is, okay, if I look at 2 different instruments or 2 different notes on the same instrument, do these limits stay the same or do they move around? And the simplest version of the theory says that the maximum force just doesn't care about what violin or cello you attach to the end of the string. Your brand of rosin can make a difference, but nothing else really matters. But the minimum force line really does depend on what you're attached to, which instrument you've got or which note you're playing. So on different notes on the same instrument or on different instruments, always the same maximum line, but you could have this minimum line in different positions. It's always parallel with this slope on this particular plot. And what makes this difference here? The minimum force is determined by how much energy the string is losing into the body of the instrument. So the more the bridge is moving, the more the body is moving at the bridge, the higher is the minimum bow force and the smaller is the range you've got to play in. And that's about to be the critical thing here. So now let's look at, here's a classic warbling wolf of the kind that I sort of demonstrated a few minutes ago. Now this is a simultaneous trace of what the string is doing under the bow and what the body is doing. It's on quite a long time scale. What you're seeing here is the warbling. The individual cycles of the note are these closely spaced little picket fence things here. So what can we see here? Well, if we look closely, so this is not now this bridge force sensor. This is a measurement of what the string velocity is doing underneath the bow. So you put a little magnet under the strings and you take the voltage off the end. And what you can see is that there are two types of country. There's stuff like this, and there's stuff like this, which is redder in the diagram. What is happening is that in this range, we've got Helmholtz motion. It's slipping once per cycle. And these bits that look denser in this rather ropey graphic that I found is slipping twice. So there is an alternation between Helmholtz motion and this double slipping surface sound motion. But then the Helmholtz comes back and you can see the double slipping starting to come back. And at the same time, the body vibration is waxing and waning in this way that you see here. Which is what you hear, of course. That's where the warbling sound is coming from, is that the body vibration is stuttering at, well, this one's rather slow. The one I played was at maybe 8 hertz or something like that. What's going on? Well, I've got a little version of that one down here. This is where we look at Shellings diagram. So what we do is that we choose to play maybe where this red star is. And you start playing your note and the body hasn't caught up with you yet, so the body isn't vibrating very much. So maybe the minimum bow force line is this bottom one here. So you're inside the Helmholtz motion triangle. But you're playing right on top of a strong resonance of the body. That's where you get a wolf note. So the body really wants to vibrate at that frequency, but it takes its time to build up because a resonance takes time to build up. So after you get your Helmholtz motion going, and then the body motion gradually grows. And what that means, as we had on the previous slide, is that the minimum force line moves up. And at some critical moment, you stay still under the red star, but this minimum line moves up through where you are and then past you. You haven't changed anything, but you find yourself underneath the minimum line. So Helmholtz motion can't continue. It must give way to double slipping. What is less obvious, but true on a good day, is if you look really, really, really closely at this diagram here, we got Helmholtz motion, then it starts doing a second slip in the middle of each sticking interval. It starts out little, and that second slip is growing, 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 growing. And it may be plausible in this figure that it's that second slip which carries on growing and eventually turns into the main slip. Whereas the one you had before, the original Helmholtz motion slip, dies away. So we've gone through a spell of double slipping, but they've switched which one is the main one. They cross over. Now, they interleave. We had the main slips and we've got these second slips that fitted into the gap. And if you think a little bit carefully about that, those second lot of slips are in the wrong phase to keep that body vibration going. They're exactly 90 degrees shifted in phase, so the body motion can die away. And that's what's happening here. See, here's this simultaneous body measurement. Here's the Helmholtz motion, and as the Helmholtz motion goes on, the body motion grows. It hits a threshold where we start getting the double slipping. Body motion carries on growing for a bit, but at roughly the time where the main original slip is decaying, the body motion starts to decay because the new slip is in the wrong phase. The body motion gets down to quite a low level, and then the body realizes, actually, you're driving at my resonant frequency again. You've just shifted in phase. Very cunning of you. But it catches up with you. The new Helmholtz motion starts the resonance growing again. And that is your warbling wolf. You've got this alternation between two types of string motion, both of them perfectly familiar to string players, just that usually you get one or the other. In the wolf, you get both of them alternating. And it's all to do with Shellings minimum force line. Okay, so that's what a wolf is. That's a classic wolf. So Shellings minimum bow force is the key to everything. So can we measure it? That's one of the things that scientists are paid to ask. Of course, I'm going to say yes, or I wouldn't have shown the slide. There is a trick for measuring this, at least approximately. We do a typical measurement. Again, you've probably seen this sort of thing before. Obviously, the picture is a violin. It would be just the same on a cello. We hit it with a little hammer, usually on one corner of the bridge like this. We measure the motion most conveniently off the opposite corner. If you can see a little bright red dot there, that's a laser beam coming in from the right-hand side of the picture, which is measuring the velocity of the bridge. So by doing that and doing stuff in the computer, you can end up with one of these frequency response plots, the bridge admittance of the instrument. And this one is a cello. This is not the violin you saw in the previous picture, because wolves are characteristically a cello thing. In fact, it is, I think, the cello I just played. It's my regular cello that I made quite a long time ago now. And you get this typical frequency response pattern. Each of these peaks, at least at low frequencies, each of these peaks is a resonance of the body. And a peak that's too high, as we'll see in a moment, is what can give you the wolf note. So now we can do a bit of stuff in the computer. We can take this measurement, and we can take the bit of theory that Schelling did for the minimum force, and we can take note by note, we can calculate what should the minimum force be with this particular instrument and your particular string. You need to know the properties of the string. And we build up a plot like this. And again, don't panic at the complication. I'm going to talk you through this in stages. So this is a plot of how the minimum bow force on that particular cello varies from note to note. Now, what are we looking at here? Frequency scale, and we're actually plotting this minimum bow force here. All the orange lines are Cs, so that it begins with the bottom C of the cello, and then an octave, 2 octaves, 3 octaves, 4 octaves. The little grey lines in between are the semitones, C sharp, D. My PowerPoint can't do flat signs, so what you might have thought was E flat is here called D sharp, and so on. So these are your notes that you might want to play. There's a separate curve for each of the 4 strings. C string starts down here at the C, the G string doesn't begin until the G, and so on. D string, A string, and they're all essentially the same curve except for a scale factor. The heavier strings scale the curve up. So the highest version of this curve is for the bottom string. And the important thing, so the biggest peak in this is your wolf note. And you count them. Here's a C, C sharp, D, E flat, E, F. F on the C string. Where do you expect to find the cello wolf? That's the note I just played you. Actually, this is a different cello, but it's got its wolf note in the same place as mine. So, and that makes sense. You think of the argument I just gave before, a really high value of the minimum bow force based on playing a steady note. That means you've got to be pressing hard enough that even when the body vibration is fully developed, you're still above the minimum force line. So the characteristic of the wolf note, it happens when you play on a strong resonance, and it's a note which is really hard to play quietly. And that's what, to make it warble like I did before, you try to play gently right on top of that note. And of course, I deliberately played on the C string to make it the worst, to make the demonstration easy. You would normally avoid, I should think, playing this particular note up on the C string. So what good does that do us? Well, we'll come to the use of that diagram in a moment. What do people do about wolf notes? Well, there are various things players do. Some of them can control a wolf up to a point by just playing technique, subtle adjustments to the bow force, position, speed, angle. There are people who like to put a sock under the tailpiece or a piece of foam or something. Or there are people who like to say, I can fix it by squeezing with my knees. So there are various things you could do. All of those things, maybe sufficiently good bow control is all right, but all of these things squeezing with your knees, putting a sock under the tailpiece. You're adding damping to the body. That does indeed make the big peak lower, removes the problem, but it will affect the whole range of the instrument. It's not targeted just on the wolf note. It'll change the sound of the instrument over the whole range. And that probably isn't what you wanted. If you'd wanted a quieter cello, you could have bought one that didn't have a wolf note. The wolf note is an automatic consequence of having a powerful instrument, pretty much, and having heavy-ish gauge strings because you want it to be loud. It's things that people want for other reasons automatically make the wolf problem worse. So we would like to do a targeted fix. We'd like to do something that attacks the wolf note without changing too much the behaviour of the whole of the rest of the range of the instrument. Well, now we have something which is very rare in the violin acoustics, string instrument acoustics world, which is that here is a real musical problem, but the fix for it is a completely familiar engineering fix that's used in all kinds of other structures. It's usually the other way around. Usually musical problems are harder, but in this case, the cello wolf eliminator, we'll come to those eventually, is an example of something that's used all over the place, and they're called tuned absorbers or tuned mass dampers. And here's an example. You can't see the absorbers yet. This, for those who don't know, London is the famous Wobbly Bridge in London. This is the Millennium Bridge, opened to a great fanfare and had to be closed hurriedly very soon afterwards because crowds of people walked over it and they got into lockstep with the bridge swaying and people were falling over and getting seasick and all of that. So it had a vibration problem to do with a particular resonant mode. So consultants were brought in, vast sums of money were spent, and they did a fix. And the fix they did is to fit a wolf eliminator. So here's a view up underneath the bridge. And you can see some things up here, not very clearly. They did several different things, but the thing that hits right on the theme of this talk. Here's a close-up of these things, and what you see is exactly a mass on some springs. It's a T-shaped mass suspended on springs. And it has been tuned to the frequency of the mode you're trying to get rid of in the bridge. How does that work? So that's how you do it. You take your structure and you add another resonator to it, tuned to exactly the same frequency as the thing that's causing you a problem, your wobbly bridge or whatever. Roughly speaking, what happens, you then try to drive it at that mode by walking over the bridge or playing that note. And of course, this new resonator you've added also resonates near that frequency, so it is excited to large amplitude. And the result of that is that you did have one troublesome resonance and you've now got two troublesome resonances. What good does that do you? Well, the good it does you is that the thing you've added is entirely under your control. So the resonator you've added, you can design it to have high damping. You don't want to make your whole cello body have high damping. It's difficult to make a bridge have high damping everywhere. That's a different problem. So your absorber has got high damping. So as I said here, because these things are tuned to the same frequency, you get two modes, but they don't consist of one of them the bridge moving and the other one the absorber moving. Both modes have both things moving. One of them has them moving in the same phase, one of them has them moving in opposite phase. And the important thing is that both of them are stretching and compressing that spring that the mass was sitting on under the bridge. And that's where the damping is. So we had one mode with very low damping. That's why there was a problem. We got two modes, but because we've achieved that by adding something with rather high damping, we got two modes that have both got rather high damping. So roughly speaking, you want something that goes thud, not something that goes ping. But it only has that high damping effect near the resonant frequency of this thing you've added. That's the sense in which it is a targeted fix. It's done very little, made your bridge a little bit heavier, but done very little outside that range. Now, I said these are used in lots of other places, and this is my favourite example. You can see what we've got here. These are competition archery bows. Now, these are a really good example of why you would want to use a tuned mass damper. think what these guys are doing. They're bending this funny shaped beam back, and then they let go. Now, the shape they're bending it back in is more or less, can you see me holding a ruler, is more or less the lowest vibration mode of that beam, which the bow consists of. So you're pulling it into that shape and then letting it go very abruptly. So of course the bow vibrates. The arrow doesn't care because it's gone, but the archer does care, because if you're doing an archery competition, we've got the Olympics going on at the moment, these things are happening, it's tiring. If the thing vibrates every time your arm gets tired that little bit more quickly than it would otherwise have done, and then you miss the next shot and you don't win. So vibration is bad. Same that tennis players don't like vibration in their tennis rackets. But in a tennis racket, we can just add damping and damp the whole thing. In an archery bow, you don't want to damp the beam, because if you add lots of damping to the main structural components of the bow, it won't spring back so quickly because it's got high damping. So you will shoot your arrow less fast for a given draw weight of bow, and that's not what you're wanting. You want the heaviest draw weight you can comfortably manage so that the arrow goes strong and true. So the problem for these archers is that they would like to not slow down the vibration at the beginning, because the arrow's gone after the first half cycle of this vibration, but they would like to kill the vibration very quickly after that. And that's where the tuned absorber, tuned mass damper, is ideal, because it's a resonator again. It takes a little bit of time. It has a transient. It takes time to realize that you're trying to vibrate at my favorite frequency. Hey ho, I'm going to vibrate with you. Oh, well, I'm going to dissipate lots of energy for you. So it's for a different reason from the cello, but it's a different kind of targeted fix. You want to help the archer without hindering the arrow. And so they all have these things. So where are they? It's not the great big long thing that sticks out in front. That's increasing the moment of inertia to reduce the kick, I am told. It's these things. All three of these bows have got a pair of things sticking backwards at an angle. You see they're here, and those are the tuned mass dampers. In one way or another, they've got a mass, and that it might be a rigid rod in a rubber bearing that gives it a wobbling resonance. Or this one seems to have got 4 bits of maybe carbon fiber or something, which again the structure has been tuned to vibrate at exactly the frequency that the bow wants to vibrate, and somewhere in the structure it's been designed in with a high damping material. And there's just a pair of them just for symmetry and to keep the balance of the bow, I expect. But I mean, you can tell this must be important because it's a fiddly extra thing to add. People spent money adding this on. But of course, sports equipment is rather similar to musical instruments in the sense that the people who really care about them, the virtuosos, are competing in a very tight market. The best archer in the world is only a little bit better than the next best archer. The best violinist in the world is only a little bit better than the next best, but that little bit matters. They're the ones who win the competitions, who get the repeat bookings. So they are prepared to spend money. Well, first of all, they will get stressed about little things, which either they think could be better or where they think one of their competitors has got a better option. And, you know, they're the ones who want their soundpost moved all the time. So it's a rather similar market to musical instruments. People care about very small details, and they're prepared to spend money and to design complicated engineering fixes to deal with something. Okay, so finally, what does all this look like when you apply it to the cello? Well, what are your options? The simplest thing and the most familiar to the eye is to have some kind of mass on one of the afterlengths. You could use a commercial thing like these familiar objects here. You could use a lump of blue tack, as Carleen Hutchins, or plasticine. Or you could place your high-fits mute rather carefully. Some people manage to do that. All those things are doing the same thing. You're taking one of these after length resonances and you're adding enough mass to it to bring it to exactly the frequency of your wolf. And you've got something which has got high damping. So this tube has got rubber or something inside it so that it's fairly lossy. Doing it with blue tack or oil clay, you're using a high loss material. It's really important to tune it. The one in the picture here suggests to me that they could have got away with a lighter one. These ones, you tune it by moving it along the length, and the mass has its maximum effect in the middle. Or to put that a different way, if you want to achieve the effect with the minimum added weight on your cello, you want to choose one that gets to the right tuning when it's in the middle. But then maybe it would have been better on the C string as well, just the beefier string is going to couple a little bit better. So you can tune an after length. Some people manage to tune a tailpiece resonance to do the same thing. That's fine. It feels like a different kind of fix. It's doing the same job. You're adding a resonator tuned to the same frequency. And of course, there are those ingenious widgets you glue on the inside, which players don't know about and makers are only too familiar with. And there are different designs, but they all have a mass and a spring in there somewhere, and they're all rather lossy. There are different ways you can do it, but each of those little things, and of course, if you're going to buy one of those, you buy the one, they tell you the tune frequency. When you buy it, you have to buy the one that's tuned to the particular frequency of the wolf of the cello you're trying to do. It has the virtue that it's on the inside and fixed. That's good if you've got it right, mainly because it doesn't rely on the player retuning it correctly when they change a string. The afterlength method works great, but you need a well-educated player to put it back right when they change the string. Or, of course, maybe if you want to take a more radical approach, you might want to say, well, what is this body vibration mode that's causing the problem? Could I make some small adjustment to the mechanics of the body, adjust the bass bar or something, in order to reduce it, the amplitude, not everywhere, but the amplitude at the bridge. What matters is how much it moves here. It's how much the string manages to lose. And that takes me on to my last topic, which is an experiment that I was involved in some years ago now, with Robin Aitchison, who some of you will know, who's a cello maker and fettler who lives just up the road from me here, and George Stepani, who is in the audience, I think, or he was. He may have gone to sleep by now because he knows all this. So Robin and George are both experienced cello makers and adjusters, and Robin brought in a cello, and we'll see, which he'd done another experiment on. I did the admittance measurement and generated this curve from his cello. And this was a nice example of the kind of blind testing we were asking. I didn't show them this plot, but George and Robin swapped the cello backwards and forwards and did the thing that tone adjusters do to identify things they thought people would grumble about. They found 3 problem notes, and I was delighted to find that they were the 3 high peaks in my plot. So we detected them. And then the reason Robin brought this particular cello is that he'd done a gluey experiment. Now, I think this is a Sam Zegmantovich invention, this idea of doing sort of post-modifications by sticking little bits on sufficiently carefully that you can get them off again without destroying your varnish. Here's the top of Robin's cello, as you can see. And I don't think he did all of these at once. This is just the full set of various straps and things that he did. The results I'm going to show are based on the 3 particular 3 straps that you see here, and an alternative intervention, which was sticking a weight onto the back underneath where the sound post is. So we have the original cello, and then we have 2 different interventions of a temporary nature. And here is the versions of the 3 charts, exactly the same as before, the original cello, the one with the straps and the one with the mass. And this reveals something interesting. The one with the straps has reduced this peak significantly, but it's made absolutely no difference to the main wolf peak, nor to this subsidiary one up here. So that particular intervention helps with one of the problems, but not with the other two. Putting the mass on the back has done the exact opposite. In this particular case, it's reduced this peak, the main peak, not a lot, but from about 6 down to about 5 on my scale. It's also reduced this one. It was at about 4 and it's now down to about 3. But it's made no difference to this one. This one's still, well, maybe reduced it a little, but this is still at kind of 4.5. So the mass helped a little with these two problem notes. The straps helped a little with those two. Different changes affected different things. And the great triumph, and of course I wouldn't be showing you this if this wasn't the great triumph, was that, again, they did the playing and did much talking backwards and forwards and decided what they thought it had done. Then I produced the pictures. And for once, the acoustics agreed with what the players found and said these are not any old players. Anyone who wants to do experiments on instrument quality, the people you want doing your test are professional tone adjusters. They're the ones who spend their life listening to tiny effects and having, knowing what to listen for when you tweak a bridge or move a post or what have you. So this was a very encouraging story. And that's the end of the story that I'm going to tell. The wolf note, that the classic wolf note to do with a body resonance is a rare example of something we understand fairly well. We know why it's there in the cello. It's because of the push to have a small instrument, but to make it loud. So these resonances tend to be a bit too strong. The physics behind the warbling is interesting in itself, if you like that sort of thing, and that's the bit with Shellings Diagram and the minimum force line moving around. Once you know what's causing it, let's say, again, rather rarely for instrument problems, we could attack this problem using a standard engineering fix, which is used in these other things. We saw the bridge and the archery bows, and all the different varieties of wolf eliminator, of the targeted wolf eliminator, are all essentially the same as the Wobbly Bridge fix. They're a resonator tuned to the problem frequency, adjusted, arranged to have high damping, and with the intention of lowering that one mode peak a little without making a lot of difference to anything else in the range of the instruments. And on a good day, we can do an acoustic measurement, which, if you're equipped for doing this has potential for being a useful thing in the workshop. I got these results quicker. It took George and Robin half an hour of trading it backwards and forwards and sliding up and down and finding notes. And I did this and said, is it at C sharp? Well, yes, actually it is. So this is one use of an acoustical measurement which has some potential for workshop use. And that's it. Thank you very much. Let me stop sharing.
All right. Thank you very much, Jim. Wonderful talk. So we have plenty of time for questions and discussion. So please use the raise hand function. It's under the reactions little icon on your bottom of your screen. All right. Okay. So Chris Dungy, you're first.
That's a surprise.
Sorry. Hey, Jim, thank you so much for your presentation. Always, I've seen it before and I learn something new every single time. So thank you so much. The peak that was affected by the straps, but wasn't affected by the mass, were you able to identify where that was coming from? What was generating that particular peak?
I wonder if George Stepani is here and awake. I wonder if he knows. The fact is, it was 10 years ago that we did this. And the honest answer is that I can't remember. I don't know if George did a modal scan on this cello. He might have done. It was done in my house here. He had all his kit with him because he always does have. George, can you remember? Did we find out what that mode was?
Not sure. We certainly did a modal analysis of more than one cello at various times.
Yeah, it's a tone below the wolf. That's where it is. So it's at a.
Well, what it would be one of these modes that's like a combination of B1 minus and C.
I mean, if it was a violin, you'd say those two peaks were B1 minus and B1 plus. Cellos are always more complicated.
Really work like that on cellos.
Yeah.
So, but normally, when you've got a really bad wolf, it's one of those combinations, and usually the one that has the largest CBR component, because that gives you a lot of mobility at the top of the bridge.
Oh yes, so, let me say a word about that, George, just because George has mentioned CBR. An anecdote, something else we did. I don't know if Murray Campbell is here. He was supposed to be listening in. A little while ago, Murray Campbell agreed to write a chapter for one of this book that Tom Rossing was putting together about science of stringed instruments, to write a chapter on viols and other early bowed instruments. And he thought, that's fine, I'll just read the literature and write a little survey of it. And then after he'd said yes, he found there was no literature. So I got a very panicky phone call from him saying, if I brought a car full of vials down to your lab, could we measure them, please? So as a result, we have the world's definitive collection of admittance measurements of various vials and rebecs and what have you. And we found an interesting thing. We'll come back to CBR in a moment. The earliest of the vials don't have a soundpost. The later ones do have a soundpost. So we measured vials with and without a soundpost. The ones that don't have a soundpost, which makes that asymmetry, have a really strong rocking mode, which is a bit like CBR, which is the worst of all worlds, because it doesn't make any sound because it's symmetrical, so it has no volume change, but it produces huge motion at the bridge, so it produces a wolf. And so my theory of the evolution of the soundpost in the viol is that it's when players started wanting to play higher up the fingerboard and they started to encounter this note where this whopping resonance was, they said, that's no good, your instrument is useless, it can't be played up there. And then someone hit on this idea of putting a bit of stick inside it and found they solved this problem. So yes, CBR can cause wolf problems, regardless of whether it makes any sound. Sorry,
yeah, by the way, Murray is with us. I think he was with us last time, and I wanted to acknowledge his presence, but then he left before I could last time. But I wanted to acknowledge his presence this time.
Yeah. Okay. Hello, Fan. Thank you.
Hi.
Hey, Murray.
Jeffrey.
Jeffrey?
Yes, thank you, Jim. That was just totally fascinating. When you mentioned, got into wolf eliminators, the kind that you put on the string. Of course, the traditional one is the rubber core and the brass with the thumb screw for tightening, and then there's more recently the solid brass ones that are have a little zigzag for the string, which produces the tension. It would seem to me from your discussion that the rubber core is what's doing the damping, and so if you make a wolf eliminator that's solid brass, is that going to work as well? I know they come in different masses, so how does all of that figure in?
Yeah, okay, as I'm not familiar with these, if people in fact think they work, then something is doing damping. What is probably happening, but I'm just guessing here, the most effective way to damp any vibration is not with rubber, but with something that gives you a frictional contact. Anything that can rub together a little bit. Friction is wonderful at dissipating energy. So I wonder if the way the strings go through it, the edges can rub together a little bit.
I think the solid brass ones just have this little V-shaped slot so that there's tension in the string that just holds it in place. Yeah. I don't think that there's anything slipping in there.
Yeah. So I would guess they work less well than the ones with rubber. But the psychology we were talking about earlier would come into play. You pay money for it, and
It's simpler. You don't have a little screw and you don't have rubber to decay inside the tube, which is one of the things that happens with the traditional ones. The rubber rots over years.
but the the oil, clay, or blue tack method is more fiddly in the first instance, but it's wonderfully lossy. So that was one of Carleen Hutchins' lasting contributions to the subject. You really need to. That's what my channel has. Looking closely at it, and you can get it in conditions adding bits as sticks until you've got just enough mass to do it and tap it with a pencil to hit the tuning. That doesn't look good on stage.
Thank you.
Chris, you have another question.
Well, not exactly a question, but I'll try to explain the idea behind the brass weights that have the S curve that's been machined into it. So the wolf suppressors that we traditionally, and I prefer to call them suppressors as opposed to eliminators.
Yeah, fair enough.
And the wolf suppressors that we're all familiar with historically are the brass tubes with the rubber insert. But those were and continue to be made with excessive weight. In other words, they range from anywhere from 7 to 11 grams. So I had suggested to the manufacturer that makes those brass weights, I had suggested to him to make them in different weights so that you could attach the weight directly to the string without the rubber insert and without the screw, because oftentimes the rubber insert was impacted to the extent that the screw would screw itself through the rubber and you were screwing directly to the string. And the whole idea was to minimize the weight. So in other words, what would happen if you could reduce the weight of an 11 gram suppressor or a 7 gram suppressor? And so over time and experimenting, it was found that reducing the weight in a lot of cases and also directly attaching it to the C string and tuning it to the wolf frequency was a better solution than attaching the suppressor to the G that had excessive weight as well as the rubber insert. So that's kind of the behind the scenes story, if you will, as to why those suppressors came about with the squiggly S machined slot rather than the round type with the rubber insert, if that's helpful for those that are interested.
I guess on the question of damping, just to do a follow-up on there, because if you just pluck your pizzicato over the string compared with plucking an afterlength, the afterlengths don't ring as much. There is more damping. I don't exactly know why, but something to do with, I mean, this other piece of string is somewhat more highly damped than the playing string, probably because of the wrapping at the end and the way it goes through the tailpiece. So there, it may be that you're getting away with the damping that the afterlength string is already giving you, even though you're not adding very much with your brass. And I see the point about the rubber is good while it lasts, but it gets worse. But I still suspect that if you could have more damping, it would be more effective for a given weight. I mean, the test is to get one of your brass ones, weigh out the same weight of blue tack and replace it with that and just try. Is one any more effective than the other at suppressing the wolf? I would guess that it'll be a little bit more effective.
Well, that's what led us to making them in different weights, was to take the blue tack and to attach it in different weights. And also I was taking the heavier manufactured weights that had the rubber insert, and I was actually cutting them down in size to see where I could go with that. So there was a combination of both the blue tack as well as the heavier rubber insert model to come up with, there was an effect and is an effect as you reduce the weight. Now, every cello is completely different in terms of what weight works the best. Oftentimes I'll see players that actually overload the whole system, so that they've added a suppressor both to the C and the G string, and there's like so much weight back there that, you know, nothing's working effective, and the cellos were wolfing even worse than it originally was. But I just wanted to at least address kind of the backstory as to where those different weights came about, and the idea with the squiggly machine slot in it, if that's helpful. They make them in for bass as well.
Yeah.
Could I ask a question?
Oh, who was that?
Joseph?
Oh, yes, go ahead.
So let's say you had a wolf eliminator, or you had added resonance that had no damping. Its effect, as I understand it, would be to split the wolf into two other peaks, but they would be at different pitches. So in effect, you may be avoiding a wolf. But would those two peaks be equally wolf prone, or would they be slightly smaller and level than the single piece? Could you just explain all that a bit, Jim?
The heights really do depend on damping. So it's it'll give you two peaks either side of the one you had with the original body resonance. How wide you split them, but then, you know, that the relative heights really does depend on the damping of the body mode on the one hand, and the damping of your extra resonator on the other hand, by whatever means. And damping is always the thing we have rather a little grip on. I was really just giving the standard engineering story that the point of fitting one of these Shellmans dampers is that it's under your control. So it tends to work most effectively if you can make it rather high loss. They do the same thing in, you know, tall buildings and earthquakes and so on. They're used all over the place, these things. And there's enough money in it that people have, you know, done. There are whole books written about this. There will be something that could look up an answer to that, but there is no short, snappy answer where I can say, yes, they'll be the same height, or what. It really does depend on the exact precision of how closely you tune them, and of the damping of the two things you started with. You remember Gaby Weinreich's paper about piano strings?
Yes.
All those years ago, two coupled resonators, and the damping of the two modes generates two modes, and their damping is terribly sensitive to a little bit of mistuning. And he was talking about piano tuners using that deliberately. That's what you're doing when you adjust your suppressor. So there's no one answer. It does depend on just where you tune it. You know, you have some control over this. And so there'll be a best place which you find out by playing the cello. But there isn't a science answer that says it will always be two equal heights or anything like that. It's rather sensitive to all sorts of things, both what you do with the tuning and details of the construction, together with the fact that these two resonators are made of different stuff. You know, one's the wooden box of a cello, the other is whatever is the thing you've attached. What about the gluing inside? Have the gluing inside things gone out of favor, or do people still use those?
People often stick them to the outside with a little bit of clay because you can move them around.
Yeah, well, that's to find the best place, but then you either don't care.
They often leave them there.
Okay, yeah, that would work. That would, that's the physicist's answer. There's a doodad, I see, yes.
Hello, has there been any
All right,
discussion about the tailpiece?
Wait a minute.
Materials?
Hold a sec. Who was that?
This is Terry King.
Can you use the raise hands function and get in line?
I'm looking for that.
It's in the reactions on the bottom.
Oh, okay, thank you.
Yeah, don't worry. We have plenty of time. We'll stay for as long as we need to answer all of your
excellent.
questions. But Seville has her hand up for a while.
Hello. That episode about the CBR and the gambas was very interesting. It explains why it's important to have the sound pores tight enough, right? The wolf gets worse when the sound pores is loose. But what I wonder is, how come the wolf can move around in pitch, given that the cello is tuned the same way on different days? Have you had that experience?
Yes. There's more. Yes. A good question. Yes. Of course, instrument. The sort of thing you've just said about the looseness and tightness of things makes a difference. The more vigorous the wolf, the wider the range that it occurs over. So actually pinning down just exactly where the wolf is in a really strong one actually depends. By playing differently, you can, the effect can be produced over maybe over a semitone or more range, and then it rather depends on your bowing details. And different players may end up thinking that the frequency is a little different, or so it's the stronger the wolf, the more sensitive it is to various things. There's a rather complicated backstory here that I don't want to try to describe. But I don't have a short, snappy answer to that, except it's one of these things that before the meeting started, people were talking about the effect of weather on overstand and string clearance and all that. And you don't have to tell me about that. I'm a lute player, and the lute relies on having a very, very tight setup with very slight clearances, because you need just a little bit of fret buzz, but not too much. And they're notoriously sensitive to the weather, I presume, because my neck is moving around a little bit as the weather changes. But those things don't usually move resonant frequencies all that far. Resonances do move a little with big changes in humidity. So if we're talking about a professional player who is in Alaska, and then the next day they land in Florida, and their instrument is going to change significantly as it catches up with that temperature and humidity change, and that's enough to move resonances around enough that you would notice it.
Something like that. Yeah.
May I ask a question? My apologies for not being able to.
Wait a minute, David. David, can you use the raise hands function?
Sorry, Fan. I couldn't find it on my screen.
It's under reactions.
It isn't always under reactions.
Oh.
It isn't on mine.
I was not able to find it under reactions. Thank you.
Can you then send it in the chat so I could sort of queue up? Yeah, so send a request in the chat then, so I can queue you guys up. Okay.
All right.
Because other people have been waiting. Jeffrey?
Okay, I'll withdraw. Thank you.
No. I'll call on you.
Thanks. I have a very short one. It seems to me that logically, since the Helmholtz diagram depends on a slipstick with a bowed string, and this is an easy experiment to do, but I've never done it, it seems like wolf notes shouldn't happen when you pizzicato. Is that the case?
They don't happen in the same way, but what you will hear, so you're playing a note on the string that's on top of a body resonance. The behavior for that is actually just like my wolf suppressor thing. You've got two coupled resonators. They couple together into two resonances at close frequencies. Now, when you play pizzicato, you pluck the string, you'll drive both those resonances. They won't be at the same frequency, so you hear beats. And guitarists will certainly talk about wolf notes. You play right on top of a strong body resonance of a guitar, and you get a note that dies away very quickly. It's very loud, dies away very quickly because the energy is being taken, and may wobble. You may hear the beats. Now, beats sound a bit like the warbling wolf note, and that did cause confusion in the literature for many years, but I think it isn't really the same thing. The process that I described with this sort of minimum bow force line moving around and so on is very specific to bowed strings. And the characteristic there is that you, with a steady enough bow hand, you could keep the warbling going forever. Whereas when you pizzicato, of course, nothing carries on forever. You may well hear some beats in the as part of the, so you pluck that note. If I pizzicato that same note, you know, F up on the C string, it'll be very loud. It'll die away very quickly, so it'll be rather unsatisfactory note. It may also have a hint of wolfiness in the sense that you will hear the beats and hear a little bit of fluctuation going on. So yes and no is the answer to that.
All right. Terry.
Yes, I have a couple of questions about the mass of the tailpiece, being ebony to rosewood to boxwood to carbon fiber to steel. Are these, you know, random adjustments? Also, the length of the string past the bridge, I mean, to actually tune it. I've done that, and that seemed to minimize the woof or take some of the edge off of the woof by tuning after the bridge, tuning it to the string above.
Yeah, I mean, there are plenty of people in this audience who know more about this than I do in terms of actually doing this with tailpieces, but it's a common enough thing. I've heard lots of makers talking about doing this. A tailpiece has several resonances. You know, you can hear some of them by twanging it. In theory, it could have 6. I think that 5 of them are probably useful for this purpose. They will indeed depend upon the arrangements of the strings and on the mass and the distribution of the mass in the tailpiece. If any one of those 5 useful resonances can be arranged to be close enough to the wolf, it will couple in the, and if your tailpiece resonance is reasonably well damped, it'll do the same job that I was just talking about with the suppressor. But in terms of recipe and what material to choose and what lengths to choose, that's not a physicist's question. That's a question for, there are plenty of people, I think, in this audience who've been doing this sort of thing for years and are well aware that you can sometimes catch a wolf. It should still be the case. I hope someone's going to be nodding sagely when I say this. I would expect, if you're doing the same trick with a tailpiece resonance, that if you just tap the tailpiece with a pencil, now you may be able to hear several notes in there because there are several resonances. One of them needs to be tuned to the wolf pitch, and the actual wolf pitch, not an octave different from it. This octaves matter here. This has got to be the actual frequency, not an octave above or an octave below. I see George Stepani's face here. He does this sort of thing. Is that, you want to add anything to this?
Yes, but I always have the benefit of having the modal analysis data, so I can see which modes are there.
Yeah.
But usually in violins, it's normally one that involves a nodal line somewhere a little bit behind the holes. So the end near the tail saddle is going up and down and hinging along that nodal line. And that is very much controlled by the tail cord length, the distance from the holes in the tailpiece to the tail saddle. And what I've been doing recently is I've been cutting my own tailpieces on the CNC machine and making them a little bit shorter than ones that are readily available, a little bit heavier. I'm adding extra mass by making the underside convex as well as the top. And this is working. It's generally good for violins to keep those modes down a little bit, because also the first big twisting mode can be a very disruptive mode and make bowing round the A0 very difficult. What else about that? Well, that's ongoing work.
Yeah.
But it's a little bit different on cellos, but that same mode can be useful. But sometimes with very short tailpieces, there are modes that you see that you don't really see on a violin, like the whole thing rotating around a point roughly halfway, its midpoint. So I think what you've got to do is look at what you've got, analyze whether or not you have a problem, and make an intervention and see whether it gets better or worse. But I think very often people are starting with non-optimally designed tailpieces. So even if you can't completely solve the problem with the tailpiece, you can actually improve it, and you maybe have to make other interventions as well. But I would say that the whole point about bringing deep modal analysis into your making is that you try and build instruments that don't need all these tweaks after you finish them. So I mean, you do that if you have to, but it'd be better not to have to.
Should we let David Burgess in at this stage?
Yes. I was going to invite David, before we
David,
get to Christian.
ask your question.
My question for either Jim or George is this. When playing a cello or a violin, is there not always, whatever note you are playing, some frequency contribution from the wolf note frequency? So if you damp that by use of a wolf eliminator or something, won't that change the sound of the instrument on every note?
Very little, I think, is the answer to that, because it's if you're playing, if none of the, I mean, if we're talking about steady notes, during transients, during a transient, you might hear something, because there you do, in a martelé transient, you might well get a little bit of initial stuff from transient response of all the body modes, and sure, the wolf mode will be part of that. If you're talking about bowing a steady note, then that's more back to the sort of things I was talking about. If none of the harmonics of that steady note are within the damping bandwidth of the body resonance, then it's not contributing anything very much. That's my guess. That's what, say, the physicists are nodding. That's what ought to be the case. But the transient thing, that the previous talk, absolutely. Can you ever hear any difference? Possibly you can, yes, because no one ever plays or assesses instruments just by playing long steady notes. The more excitingly transient, vigorous the bowing is, the more scope there is, perhaps, for these things having an effect everywhere. But the intervention that's enough to suppress the wolf doesn't have to be all that big. I mean, the pictures we were seeing, we reduced the height of that peak from 5 to 4 on some scale. It's not making you want just enough that you can bow the note you want without it warbling. But any intervention wants to be the minimum. I suppose that's really all I'm saying. It pays to have all interventions minimized.
Would George Stepani be interested in responding to my question?
George?
No, I wanted to pick up on the effect of having the effect of wolf notes on other things. I think that is his question. We did some perception experiments at one of the V4VAR workshops, where we looked at the height of the minimum bow force on various cellos, and some of us found we could actually identify them by the starting transients. So what we thought is that the instruments that had a big minimum bow force peak actually had starting transient problems on other notes as well, which is an interesting correlation. So in a sense, though, that I mean, the instruments work a bit like a finite, impulse response filter. So you're repeating the complete impulse response at time intervals, so that when it's not perfectly periodic, then the effect of that minimum bow force is probably there. But that's, as far as I know, that's about the only work that's been done on this.
All right. David, are you
Well, it's just that
satisfied with the
experiment,
answers?
and that's what we observed.
Yes, and I'll add that what I've observed is that we can't put any sort of wolf eliminator or damper on a cello without affecting the whole cello. I'm open to counter opinions, but that has been my observation.
Jim? Well, okay, I guess he's not going to respond. So let's go on to Christian.
Yes. My question is a little bit similar to what David Burgess asked. It's I have the feeling that today in the market we have a lot of wolf eliminators working very well, but absolutely killing the high overtones, the interesting harmonic in the sound, not only here the wolf note, but in the whole range of instruments. And what is acceptable to a more modest player for not have the trouble of the wolf note, it's absolutely not possible for a bass player because they don't want to not have this overtone just for not have the wolf. So, and my feeling, no, I'm only making new instrument. I'm not restorer anymore, but it seems that the better my instrument, the more problem I have with wolf note. It's become more and more, probably because the body of the instrument is more efficient to respond, but it's, I don't know if people here, violin maker, have the same problem, but it seems that the better the instrument, the more prone to wolf note they are. And I try everything in a peripheral thing like fingerboard, tailpiece, or type gut. Really, it's really structural problem of the instrument. It doesn't seem to have any importance what we change around. So this is my question. Does these wolf note are really connected to an efficient system?
I think what you're saying is what it would not disagree with anyone. Yeah, if you, at least any loud instrument is likely to have a wolf note, and the cello suffers from it famously because it's undersized. If you remember the Hutchins octet, if you scale a violin up to the size, to the tuning of a cello, you get a bigger instrument, which will be less plagued by wolves.
I have terrible problem of wolf note on my violins too.
Yeah, so because the cello is made smaller or tuned lower, depending on your point of view, than it really wants to be, that automatically raises the wolf problem. It's a well-known problem with the scaling. The lower instruments, the viola is worse than the violin, the cello is worse than the viola. Bass is a rather variable quantity, but it's governed by this minimum, and that comes directly out of this minimum bow force kind of idea. The strings are coupled more closely to the body in a cello than in a violin, which means all of these problems with the body vibration interfering with the bowing process. That's what we're talking about. The wolf note is the body vibrating more than the player really wants it to, and it's interfering with the tight control over bowing. But that's the price of having a loud instrument, particularly a powerful instrument, and without making it bigger. You could either compensate the loudness in some other way by making the body bigger or by having a bit of subtle reinforcement with loudspeakers or something, or you're rather stuck with the wolf problem because of this undersized nature of the cello. Yeah, whether all interventions, I don't entirely the thing you said about losing all the high frequencies, that I can't see offhand a good reason
The
for
NAS is
that.
part of the sound. The overtone, what many musicians are looking for, is this ringing part of the sound.
Jim,
You
can I add something to that? Because in some cases, if the weight is very close to the bridge, the thing is that you've got damping over a much larger range of frequencies, and you've actually added effective mass to the bridge as well, because you know the dollar mute, right? You basically, if you play some mass very close to the bridge on the afterlength, you've increased the effective mass seen by the bridge as well. So there are these, depending on the interventions, you're not just producing damping at the wolf note frequencies, but you could be either producing some damping at other frequencies or adding to the effective mass of the bridge.
Yeah, true up to a point. That it's rather a subtle question. That, I mean, from that point of view, the little glue inside things should be the least disruptive. But you think all of those little gluing inside widgets, people immediately notice? I mean, it'd be interesting to do a blindfold test. People think they can notice. Can they actually tell when you take it on or off?
Of course, of course.
But have you done it as a blindfolded test?
No,
What we were talking about earlier.
Do you mean?
Use the action of all the sound. Sorry.
Jim, do you mean, can you tell if it's suppressing the wolf?
No, this claim that any kind of suppressor changes the sound of the instrument significantly across the whole range. I think it would be interesting to do a blindfolded test with you have a blindfolded player and gluing one of these things on the outside, therefore, where you can just pop it on and off randomly and just see if they can actually, so they try it once with, once without, and then you give it the third time where it may be there and maybe not there, just to see whether they can in fact immediately say, yes, it's there, no, it isn't there. And, don't let them play near the wolf note. Play high up. It will be interesting. Maybe they can, but it will be interesting to prove it, because there are plenty of examples of things that people were sure they could hear until someone actually did it, like gold-plated loudspeaker leads in your hi-fi. There are people who swear blind that they can tell when they've got gold-plated cables for their loudspeakers, and they can't. Electrons don't care, but you pay more for it. It looks good. The shop assures you that it's going to be good. So it sounds good.
I did that test with Scotch once.
Jim, yes, I have done blind tests.
Okay.
Well, I think, Jim, it's a question of degree. I mean, we know that in certain types of interventions definitely do go beyond just the wolf note, and then so the question is, with some of these other interventions which are more subtle, which some people claim that definitely does cause effects, how big really is that effect, and are really people truly experiencing it, or it's some through other means that they think that it's causing it. So I'm just going to leave it at that.
Sure. I mean, I think it will be interesting, and maybe David has done this, to do that experiment with one of these tailpiece modes. Now, you've always got a tailpiece. It's always got the same number of modes. All you're doing is shift, so you're not adding something you didn't have before when you adjust a tailpiece. So just by adding a little bit of mass on taking it off a tailpiece, you could move one of these tailpiece resonances on and off the wolf frequency, but it'll still be there and be pretty similar. Now, are you saying that when it is tuned to the wolf frequency, it kills the tone over the whole range? Or are you actually saying that why can't we make cellos without tailpieces, because having those tailpiece resonances always kills the tone over the whole range? That will be an interesting question to explore, I think.
I'm not talking only about cello because I have a very big problem with violins too. So it's not specific to cello, it's cello and violin in my case. And the problem with this valve suppressor, the one who affect less the sound are the one with the after length of the string. But they are a little bit less efficient, for example, than the Kranz system with a magnet. You put more or less behind the F hole. It's very efficient for the valve, but not for the sound. So everything in the body of the instrument are more efficient, but kill more the overtones and the after length who are less efficient, but kill less of the sound. So yeah, tailpiece, I've been trying so many things, so many tailpiece, so many. I'm not sure there is a way to go around here, but why not? Why not try? And it means tuning certain parts of the tailpiece with the frequency of the valve.
Yeah, that's what George Stepani was talking about. In that you could imagine doing quite a clean experiment with that and see, but okay. I'm just guessing.
Okay, let's move on because we have a lot of people with questions or comments. So Anders.
Do you hear me?
Yes.
Hello. Yeah, I have two things I want to mention, and one thing is from the last time we talked a little bit about the double bass tests we did with Knut Gittler and Anders Askenfeldt, and one of the things we did at the music school here in Oslo was to drill a hole in the floor, stage floor, and during a break there, I measured the bridge impedance of the double bass with the pin on the through the floor, and then later with the pin on the floor, and it was quite a big difference between those two bridge admittances. And later on, we've seen Chris demonstrate a plate of kind of heavy plate put on the floor, and the valve moved on the cello. And I do not do much work on double basses and cellos and so on, but Jim has shown here that the bridge admittance is very important and might carry very important information. Maybe there is a coupling to the floor or to pins and type of pin ends, rubber or not, and so on. Things to work on there. I don't know. And then about the humidity. I've done some crazy tests at my bathroom here with 10 instruments and taken them up to 85% humidity, and it was impossible to play them and so on. But that aside, you know, wood, the wood stiffness parameters changes with the humidity content. The damping changes with the humidity content. The size and proportion of the wood pieces changes with the humidity content. And we know that some instruments might need a sound post for summertime, and different sound posts tighter for for wintertime. And you know, when a shell changes its shape, then the resonances moves. So I think one of the reasons that resonances move around in instruments is the humidity and the climate changes. But I don't know so much about it in reality, but I'm very interested in the topic because we have in the wooden construction industry, this is a topic as well for cross-laminated timber and strength and so on. So there is some literature out there, and also finite element calculations done. It would be great to do something similar on a violin to see actually what is moving when you change the humidity content. So that was I have one question to Jim. If you have coupled resonances, do they share the damping then?
Yes. Yeah, that's a yes. Usually, yes, but yeah, that's the short answer, which is usually correct. Ask me offline about the long answer, but this is Garby's paper on the coupled piano strings shows some of these effects. There are various things that can happen when you couple things, but usually, yes, they share the damping.
Okay, thank you.
Yeah, so Anders, a couple of years ago, we did do measurements at the acoustics workshop on cellos and the effects of the termination in conjunction with, Chris Dungy's experience of, was it basically very rigid concrete floors, minimize the wolf, and so we did find that yes, the floor, the nature of the floor can affect the main modes. And actually, Colin Goff, who probably knows most about it, is unfortunately he had to leave early for a concert. But I don't know if George Stepani or Evan Davis wants to comment on this.
Yeah. So in my VSA talk earlier this year or last year, whatever that was, has some of that data in it, and that's archived someplace.
Yeah. Okay, let's go on to Andreas.
Hi. I have a basic understanding question to Jim. To Jim and to George. I perfectly understand that if you add damping somewhere at the after length, or some people to do some some blue text somewhere and whatever, that this will if you tune in after length or in another external damper which has damping effect. So if you tune that to the wolf frequency, I totally understand that this will positively bring down the wolf or split the wolf or whatever. But in my understanding, it's not clear why tuning of the tailpiece can why this helps, because in my mind there's always, okay, the tailpiece is going this way, and if you now happen to tune the tailpiece to exactly the wolf note, in my understanding, you will certainly enhance the wolf note, so it will be stronger. So what is the missing part in my head so that I can understand that more clearly?
Everything does depend on damping, but for these, it depends whether your tailpiece mode pings away, you know, how well it's true. Coupling an undamped resonator to your wolf is not going to do any good and might even make things worse. That could be true, but nothing is undamped. Damping is something we never understand all that clearly, and you always end up having to measure it. Tailpiece resonances, are they more or less damped than body resonances? I don't know off the top of my head. George will have data for this, I suppose.
I think, Jim, generally speaking, the tailpiece modes have rather low damping.
Right, in which case I'd agree with Andreas that coupling a lightly damped resonator certainly would, on the face of it, has the potential for making things worse rather than better.
It's a funny thing, Mike, by introducing another resonance, you can do something to an existing one, and you might well make it better but it's not always necessarily the case that you want to tune your eliminator to exactly the frequency. You may want it a little above or a little below. You kind of just disrupt it in some way. And obviously, if you're introducing damping, that's going to help bring the peak down. But there certainly is an effect of having of the coupling, the tailpiece modes. By moving them around, you definitely change the way the instrument feels to play.
Oh yes, everything has an effect.
And I think if you get rid of the tailpiece altogether, you won't like it. So those or neck fingerball roads, like, you know, you may say, well, what the hell are these things doing? They're kind of parasitic resonances. You know, some people say, well, I want to make the neck stiffer, get rid of all the neck resonances. But in fact, we would like our instruments less well if we removed all of those substructure couplings. But I don't know. It's very difficult to set out a set of rules for what you should do. I think, you know, it's a matter of assessing the instrument, looking at what you've got, seeing where the possibilities are, and then you move from that, rather than following a rule book.
Yeah. So to summarize, because Jim, that was one of my questions. I think your answer. My question is: at what point does adding another resonance make it better or make it worse? And I think your answer is: it all depends on the exact situation.
That's a safe answer. Yes, I can agree with that. I mean, really, it's not my business to talk about better and worse in terms of instrument quality. I can talk about better or worse in the sense of minimum bow force, you know, something I can measure. Does it make a peak in my minimum bow force measurement go up, or does it make it go down? But does that have knock-on effects which in other ways people don't like? Those sort of questions are always very difficult. I never claim to have answers to that kind of thing. The only way to know is to try it. Because, and as people have said in other contexts, yeah, you've got a complicated system. You change anything and everything changes a bit. We're rather tuned in to those fine details. Some of those little bits matter a lot to us, whether or not we can actually hear them. So yes, absolutely, there definitely may be. That's the answer to that.
Joseph, did you?
Yeah,
ahead,
I just wanted to address something that Andreas asked. There's a notion that you have a tailpiece resonance and then you could tune it till it matches the Wolf resonance, but you can't because, well, as Colin likes to explain it, the two veer away from each other. You can never get them the same unless the two systems aren't coupled. If they're not coupled, you could match them and it wouldn't have any effect, but there's no way that a tailpiece resonance isn't going to be coupled via the bridge. Isn't that correct, Jim?
That's true, but that's true of all these Wolf suppressors as well.
Mm-hmm.
When I talked about tuning it to the same frequency, you tune it close enough that it's when you're in the middle of the veering process, that's when it shares the damping and when you start to do some good. Yes, you don't ever get the frequencies exactly the same. That's a slightly, let's say you create two resonances and there's a limit to how close they can be. But if you add some damping, and that would, the tailpiece is no different from an after-length resonator or a glue inside widget or a neck resonance or any of those. They all behave the same way.
But I think there's one practical difference is that resonators you can remove, then you can check the tuning and put it back on. With ones you can't remove, you can only do it by, you know, turning the knob one way or the other. You can't tune it and then apply it because, you know, they're pre-coupled. You can't take the chin rest off and tune it, or the tailpiece off, because it doesn't exist in that. The resonance doesn't
I guess you'd have to do one of these burying the body in sand experiments, but that's not super convenient. Sure, but that wouldn't stop you doing a blind experiment if you can get a tailpiece so it's doing something you like, and then you add 2 grams of blue tack and it stops doing the thing you like when you can see it, then it would still be interesting to do the blindfold test of where you don't allow people to play anywhere near the Wolf note, just to say can people in fact perceive a change of sound quality over the whole range? That's an interesting question, and I don't know the answer to that.
I think that Robert Cower addressed that in the chat. Fan, do you want to bring him on? He did a blind test.
Actually, he had a couple of things. I can't find. I can't find it right now.
He said that he puts a one of the internal wolf suppressors in every cello, and when people try them, if he tells them it's there beforehand, they say they can hear the difference, and if he doesn't tell them, they can't hear the difference. But he puts one in every single cello he sells.
Well, he says, when I told people before if it is there or not, I get lots of opinions, usually negative. But when he does it blindfold, nobody knew the difference. So, okay. Let's go on to Christopher Dungy.
Well, I think, was Hans Johansson before me or after?
According to this Zoom, which stacks it up in the order that it raised hands, you're before Hans, but you can defer to him if you want.
All right. Well, I just wanted to shortly say every piece of the cello matters in terms of how successful your wolf suppressing will be. And meaning your whole setup. In other words, it's not just a body issue. It's the fingerboard, it's the neck, it's the bridge, it's the tailpiece, it's the after string length, it's the end pin, it's the end pin into the floor. So I'm mentioning this to those makers that maybe haven't spent enough time looking at all of those variables individually to address the overall wolf issue that they're getting. My whole approach over the years from cello number 1 till cello number 126 was all of my cellos will have a wolf, but what can I do to minimize it? What things can I do in the making process, in the adjusting process, that will be the least invasive? And there's numerous ways to address that. So I just wanted to encourage those makers, if they haven't spent a lot of time experimenting with all of the variables that are out there, as well as coming up with your own approach, it's doable. You can get to that. And then to address Jim's minimum bow force, the better players like Jeffrey Solo, like Lynn Harrell, like Yo-Yo Ma, any of the great players can play any cello and not get a wolf. And what I'm getting at is that if you have such a high level of bowing experience, it is possible to have a cello totally naked, meaning no medication, no suppressing. And it's totally possible by those great players to play an instrument without that suppression in place. So what that says is that we all need to work on our minimum bow pressure to arrive at those results, because it is possible. I've heard it, I've experienced it, and my hat is off to all of the great players, Jeffrey especially, for achieving that result.
All right. Thank you, Chris. Hans.
Hi there. Hi, Fan.
Hello.
Hi, George, Jim, and everybody. Yeah, I'd like to, I really enjoyed hearing what Joseph said about the effects of coupled resonances, because resonances are really, to my mind, my understanding, mutually disruptive. So you cannot, it's like listening to the clapping of one hand to center on the resonance of the body and then the resonance of a wolf suppressor. But my question to, well, maybe Jim or George or you, Fan, is, I couldn't be here the whole time, so I don't know if you covered this already, but degrees of freedom of wolf suppressors. We obviously, the string is vibrating in actually kind of, I mean, seen from the bridge is vibrating in kind of 2 degrees of freedom, really, horizontally, vertically.
Yeah, the after length things will have two. Normally, they'd be at pretty much the same frequency.
Yeah.
So that in itself doesn't make too much difference. On your question of how you tune things, the trick, if you want to tune separately, is to stick a practice mute, heavy practice mute on the bridge while you tap the after length, just to cut the coupling down. You can cut the coupling down a lot with just a good mass on the bridge. So, you know, you can go, you can never get rid of coupling, but you can reduce it,
right, yeah,
to get closer to getting the thing you want.
But when you take the practice mute off, then you have an interaction always between the two of them.
Absolutely, but that's the interaction you want. It's that interaction which shares some of the damping.
Okay,
The interaction is what you want. You want to be right in the middle of this veering range, so that you are adding some damping to the body resonance. That's exactly the thing you're trying to do.
Right. My question, basically, my main question was whether 2 degrees of freedom are enough for a wolf suppressor.
Oh, plenty. I mean, one would do. If you're only trying to target one mode, you only need one degree of freedom, provided it's moving in a direction that couples reasonably well.
Right.
So it's, you know, if it's moving the top of the bridge in the plane, your degree of freedom that matters in the after length is moving that way as well.
Right, but the degree
so
of freedom,
it's, I mean, in terms of that, I've talked about these engineering applications. These things are used for all kinds of things, and people do make things with more degrees of freedom and design them so that you can attack 4 or 5 modes with one device.
Right.
So yeah, that can all be done. It's not usually an issue in the wolf world.
Right.
Yeah, Jim, it seems to me that what's perhaps more important from than the degrees of freedom is actually the impedance levels, which determines how much energy gets transferred, you know, between the elements, not just only at the wolf note, but at the other frequencies. Because, you know, one of the things I want to point out is that the importance of the afterlength and the tailpiece resonances isn't that it's seen at the bridge through the end pin and the body, but that when the string vibrates, the whole tailpiece assembly, anything attached to the afterlength, a significant amount of energy is actually seen directly at the bridge where it's connected to the bridge, and therefore, and also to the string, the vibrating part of the string that you're interested in, you know, playing at the other side. So there's a huge amount of energy coupling between, you know, the bridge is not a perfect termination for the vibrating string. Not, you know, 100% of the energy of the string doesn't get reflected, you know, back just through the string and down to through the bridge. A significant chunk of it, you know, and goes back and forth through the afterlength as well.
Just making heat.
Well, my point is that's why this is complex, because when you're dealing with adding wolf note suppressors attached to the afterlength and the tailpiece assembly, you know, people talk about resonance of the tailpiece, but I think it's more accurate to talk about resonances of the tailpiece assembly with the 4 strings and the gut, you know, attached to it. So it's quite complicated.
Yeah. Okay, thanks. That was it.
Oded? Unmute yourself. Oded, you need to unmute yourself. There you go.
Greetings, everybody. Can you hear me now?
Yes.
Yep.
Okay, I have a non-technical question. I got into a discussion with some people about how a wolf tone works, and they had looked it up on Wikipedia, and Wikipedia seems to be stating that the wolf tone is caused by a standing wave. It's very difficult to argue with people to convince them that Wikipedia is wrong. I wonder if anybody knows, or perhaps somebody can take up this issue and deal with getting that changed. That's it.
Yeah, good idea in theory. you can spend your life trying to correct things. Wikipedia is great, but you need to be a real enthusiast to want to fix things. I mean, you're right. If it's got something misleading, then that's a pity.
Yeah.
Yeah, Jim, it says, well, yeah, it's not a good, I'm looking at the Wikipedia wolf tone. It's not a good explanation. So
yeah,
I don't know if you want to take the time to fix it.
If you're trying to convince someone that you know what you're talking about and they go to Wikipedia, you look like an idiot.
All right. Noted. Thanks, Oded.
Thank you. All righty. Nice to see you all.
Marty.
I had a question about string tension. Are you better off with lighter tension strings?
Yes. From a wolf perspective, yeah, absolutely. The string impedance compared with the body impedance is what matters. Yeah, anything that makes the instrument louder makes the wolf worse. Anything that makes it quieter is going to help you.
Well, a similar question. If you have a choice of neck length, string length, are you better off with a long, lightweight string or a short, heavy string?
Long, light.
At the same pitch.
Yes.
I'd have to do the arithmetic for that one. I mean, are you keeping the tension the same?
Yes.
Are you just changing the weight? Okay, if the tension is the same, then the impedance is the only thing that matters. So light is good from a wolf perspective. It's the square root of the tension times the mass is the impedance of the string, and that's what scales those curves. That's what makes the difference between the four strings of the instrument.
Right. Okay.
David Politzer, I somehow you dropped down, but I thought you were higher up on the queue, so I'm going to call on you now.
Well, thank you. I keep changing my mind because anyone who knows me knows I've built instruments, but none of these under discussion. I don't play them. So it's just book learning, but I like to make peace. One is, Jim says, a crucial thing he said is that the resonance that you're adding, there's an issue of whether it couples well. And it's just in that word well, which then makes him actually agree with the builders and the instrument experienced people that whether certain kinds of interventions can have more effects than others, right? So there's a hierarchy as we try to understand musical instruments. Of course, the whole instrument just has normal modes. That's one way of thinking about it. But we divide it up into parts because of this hierarchy of who kind of works the way it does separately. The obvious one is strings, right? And if you're talking directly to the bridge, just the bridge, that's more direct than putting a glob of oobleck on the soundboard, which while it might change one resonance to the right value, it will change them all. And that's what I think some of them hear. I also don't hear very well anymore. The other thing which confuses the discussion when you make contact with physics, just last thing to say, is that sound production is an important source of dissipation to the instrument. And you're not interested, well, you're very interested in sound production. So there's a trivial statement, but somehow separating those considerations off from someone telling you about damping, that's an important thing to do and a source of confusion, at least for me. So thank you for calling on me. I kept putting my hand up and down. It's my fault.
Okay, for those who are not aware, and hopefully this won't embarrass him, but Professor David Politzer is professor of physics at Caltech, and he's a Nobel laureate. So,
which means you should understand the simple harmonic oscillator. That's
by the way, I
yes,
actually,
I know. So you tell them, not me.
No. I wasn't going to say it was just a personal comment. I actually took physics from Professor Pollitzer when I was a freshman at Caltech. So, but you cannot blame him for all the stuff that I didn't learn properly. That was my fault. Andreas? You're muted. Can you find the unmute button? I think he's trying to. Oh, there we go.
Yeah.
Okay.
Hi. Just one last question. Some years ago, there was on the internet there was a very nice video. I think of some Viennese search lab showing normal cello string motion in slow motion, and then showing that the same motion with a wolf note, and it was totally impressive. But I can't find it anymore. Do you happen to know where it's gone, or where I can find that, or do you have a video like that online?
No, I don't have any. No, there have been various high-speed movies of showing Helmholtzs motion and what have you, bowed string motion, but I think you'd have to be rather careful. They all work by strobing a wolf note. You've got these two different time scales. You've got the sort of note time scale and the warbling time scale. You'd have to be rather careful to represent the behavior correctly. Otherwise, you could get something quite misleading, I think. Pretty, but misleading. The world is full of things that are pretty, but misleading.
Okay, yeah. I think this was really new for me earlier tonight when you told that the second movement takes the role of the first, because of course that was not shown by this stroboscope thing. It was shown that there was an original moving, and then it stopped, and the bow had totally different difficulties in moving everything, and then it started again. But of course, your explanation was way more profound. Thank you. But it would be nice to find anything like this, and as video to show customers what all these matters is about.
Eventually, I'll get to this bit of my ebook that I'm gradually writing. I haven't got to bowed string things, but when I get to that stage, I'll certainly think about. I'm using animations wherever I can in that, but I haven't got that far yet.
For now, Andreas, you're going to have to tell them to watch the beginning of this video and Jim's talk, because it's absolutely true, as people pointed out there. Most of the explanations on the internet of how wolf notes work are misleading or just downright wrong. So that's why we've given this talk and we've repeated it again. Let's see.
I also wanted to add that the last Oberlin Acoustics that was held live, we actually had a high-speed camera, and we videoed the effect of the wolf note and what happens to the string in the bridge. And it's an ongoing project. I also wanted to put a plug in that our next Oberlin gathering, which might take place in 2022, is going to continue on the subject of cello wolves. So all of those makers out there that are puzzled about cello wolves, please come next year if we do have an in-person gathering, because it's going to be focusing on the cello wolf and the continuation of that information that we're still missing. Sorry for the infomercial here.
Thank you, Chris. We're going to the other Chris Sandvoss.
Hi, thank you so much, first of all, everyone, for the wonderful information. It's always inspiring to absorb and to think about all the things that have been said. I just have a quick question, and it's probably an obvious one. It relates to the shape and how the things have been constructed in the past and how we haven't deviated from the form. But why is it always that it's the second or third note on the second string? So, you know, there are a few abnormalities, of course, if there's a frequency of a fingerboard or so on and so forth that wrecks things. But usually it's the F or the F sharp or the C or C sharp on a violin, you know. So any thoughts on why that is, other than the obvious?
I don't know if you were in the last of these talks when Evan Davis was talking about things, but something that struck him and strikes me, that those of us who've done vibration measurements on other structures than musical instruments, that the most striking thing when you see 20 violins or 20 cellos measurements plotted on top of each other is how very similar they all are. That for in any other structural world, you'd say, well, those might just be measurements, repeat measurements on the same structure, we'd believe it. So really, any decent violin or any decent cello, you're only allowed by the market to deviate within rather small ranges. Otherwise, it'll still be a musical instrument, but it'll be a different one. And you reinvent the viola da gamba or whatever it may be. So I think really the answer to your question is that those main body resonances, which is what we're talking about, I mean, in the violin world, it would be this B1 minus and B1 plus, and they vary a little bit between violins, but not very far. Otherwise, it ceases to be a violin. And those resonances govern where the wolf is, more or less. So it's, you know, any normal cello made as a Strad copy, you know, will tend to have its resonance, and that's kind of F or F sharp position, because it's always more or less the same mode. George would have something to say about that, probably. So I think it's one of the frustrations of doing science on these things, that actually the first step is of no interest to all you maker guys, which is when we look at the data room and say, well, these are all essentially the same. And in any other structure, all violins are more or less identical, would be as much as you'd want to know. But you really, really, really care about the small differences that are left. So you're spending all your time fine-tuning things which in absolute terms are rather subtle, but your clientele has learned to care about them, and the music repertoire cares about it. But the wolf note position is one of these things that arises from the kind of conservatism of the design, that if you're too far away from F or F sharp, people are going to say, this is a 3/4 or something. You know, a small size cello will be in a different place.
So Jim, the other thing, if you could explain, is why the wolf note typically is worse on the same note on the lower strings as you go lower.
Yeah, absolutely. That's an easy one. That goes back to my charts. It's the impedance ratio, the impedance of the string compared with the impedance of the body. The impedance of the body is the same whatever string you're doing. The heavier strings have got higher impedance. So just typically steadily across the range. In the string, well, Fan will know about this. His day job involves making strings. String makers don't have to make sets of strings. I mean, they could make things with constant tension. They could make things with constant impedance. Your typical set of strings has higher impedance on the lower ones than on the higher ones in the bowed instruments. That's what we're used to. You could choose different gauge settings, but with a regular set of strings, you just use heavier strings, roughly the same tension but heavier, and that puts the impedance up. That's why, I mean, you said the note's always the second note on the D string, but to demonstrate it, I played it high up on the C string, because that's where you get all these star players. And you say everyone can manage to play around a wolf, but I bet they don't often play that F sharp high up on the C string. They will choose to play it on the G string, where it's easier to control. And that will be part of the deal of being a great player, knowing when to avoid a trap. So I guess that's the short. That makes sense?
Well, it does. I mean, we're sort of talking around all the same things we've talked about before. I do appreciate the clarification further, but there has to be, in a clear physical sense, there needs to be a coupling between the bridge and that particular part of the top. And I said in the beginning, it's very simple. That's the structure. I totally understand that. But if we're looking at 3D modeling, or not even, if we do a slow analysis of everything, is there always that particular spot? And I just picked those notes because they're obviously different, but they will be across the board the same. C sharp or F sharp. And violinists have to play C sharp when they play the solo repertoire up on the G string. So it's a very problematic note for violinists, as a matter of fact. That's the most difficult ones on the G string. So having said all of that, if under infrared, or I don't know how you would measure it, but is there the consistent coupling between the bridge, the driver, and a particular spot on the top, and we know where it is underneath the F hole, but
it's not a particular spot really. The mode that causes it's these things called B1 minus and B1 plus in the violin. The mode shape is always roughly the same in most normal violins. And it fills the whole of the top, the whole of the body is vibrating in that mode. Everything is doing something. Nearly every, there are nodal lines, but there's nothing really about particular spots on the top. There are particular spots on the top that are not vibrating, and that would be the place you definitely wouldn't want to stick your suppressor. But the top is vibrating nearly everywhere.
I disagree. I disagree. I'm sorry. I politely disagree, because if it would be vibrating everywhere, then equally, then we wouldn't have a wall.
Not equally.
There's a particular driver that is in the top that vibrates beyond everything else. So there must be a direct connection between the bridge and that very particular spot.
It's still not. The amplitude varies. You need to see some of George's mode shape pictures, I guess. I don't have these sort of.
Can I, Jim? Let me see if I can try to understand Chris's point here. I'm going to simplify because there are different resonances, different modes, in the body. Typically the largest one, at least on the violin, is the B1 plus, and that's where the overwhelming majority of the wolf notes occur on the violin, is on that particular frequency, because that is the largest resonance. If we measure it both by acoustic output, typically that's the largest peak we see, and by the bridge mittens, which is what the string sees in determination. And at that frequency, the bridge is moving the most. And that's what determines how severe the wolf note is.
Yeah, that's right. The only particular point which is important is the top of the bridge, as you say, where the string notch in the bridge is the only sense in which there's a particular point that really matters. And then really that's why a suppressor attached to an afterlength is rather effective, because it's acting through the bridge at the place you're most interested in. If you're thinking of sticking something on elsewhere, then absolutely it matters where you do it. When I said the whole top is vibrating, I certainly didn't say it was all vibrating equally. It's certainly bigger in some places than others, and it would pay to choose somewhere that was more vigorous than not. There are animated pictures out there of what this B1 plus mode shape looks like. So there are regions of the top and of the back which are vibrating quite vigorously.
Does that address your point, Chris? I'm trying to understand what
it allows me to think about it in I have to imagine being right. It's like the plumber imagining being the water. So yeah, I appreciate it. Yeah, thank you. I'll look into it further. I look forward to further discussions on that. Thank you.
Okay. Gosh, we're back to the repeats of questions. Anders.
Yeah, I wonder how close can you put the in some way tune the wolf note to be in between played notes on the cello? how close can it be? How close to the resonance do you need to be before you get the wolf going?
Within a half power bandwidth would be the technical answer to that, I suppose. So we're talking about a Q factor of 30. So, I mean, it presumably does help if you place that strong resonance, not, halfway between two equal tempered semitones, but I bet it doesn't make all that much difference. There's enough transient stuff and sliding around and vibrato going on that something will cause a problem. That would be my guess. I mean, when my sliding the finger up and down to do the demonstration, you can get the wolf effect over. I guess that's the answer. When you've got a really good vigorous wolf, it causes bowing problems of at least a semitone.
Okay, Jeff. Yeah, somehow, Jeffrey, when you're unmuted and Jim is unmuted, we get this echo. So, but I know you want to comment on this, so go ahead.
Yes, I was just going to say that when you have a wolf eliminator that's on the string, not only moving it around adjusts the intensity of the wolf, but you can, as I noted in the chat, you can push the wolf around to a certain extent. So cellists are used to adjusting the wolf away from the pitch that they have to play in a certain piece by just moving the wolf suppressor up and down. We just kind of deal with it the best we can deal with it.
Thank you. Andreas? Oh, wait, are we finished with you, Anders? Okay, so let's go on to Andreas.
Okay. The wolf note is a big thread. So there's one more question. Some people swear they can do something if they tune the fingerboard by putting asymmetrical weights on either on one end of the fingerboard. They say, oh, it's a secret, and I sometimes do it. Is there any scientific thing behind that?
My guess would just be, if it works, it'll be by the same mechanism of tuning some resonance or other fingerboard twisting mode or something.
If I could just cut in, it's definitely, you can get a fingerboard twisting mode, but it's usually a little higher than B1 plus. But if you could bring that down, it's do the same thing as tuning the tailpiece.
Yeah, but not very effectively coupled. I'd have thought a fingerboard resonance doesn't seem a great way to do this if you don't want to affect anything else very much, because it's a long way away from where the action is.
You can have a very large amplitude, so I think it does couple quite strongly, yes. But I think it can be, you can see it in that it can call a splitter mode if you bring the two close together. And for lower down, if it's in your B1 minus, the scroll rotation mode is very strongly coupled. So yes, there's potential there, which is why I say you have to look at what you've got and then see what is an option. So if that resonance is very far away, you're going to have to do something ridiculous to the neck and fingerboard to bring it down. So you need to look somewhere else if that's the case. I won't go on about it. I'm muting myself again.
Is it possible just to plug or whatever the fingerboard to get that resonance, or just only by model analysis?
If you've got a good enough ear, you can probably hear it. I mean, you don't need full-blooded modal analysis. I mean, I have a little FFT app in my phone. I'm sure I could hold my phone up to the fingerboard and tap it with a pencil and find that frequency. So quite low-tech methods would do to tell you whether you're within striking range of something useful.
All right. Gosh, I think for the first time, we don't have any hands up. Are we talked out of? Well, Marty sort of has his physical hand up. Marty, did you want to say something?
Do wider feet, bridge feet help reduce the wolf? Anybody?
I don't know is the short answer. That if they make a difference, it'll be because they couple differently to that B1 plus mode of the top. I mean, certainly the spacing of the bridge feet will make some difference to how strongly that particular body mode appears in the bridge. I mean, in an extreme, if you could put both feet of the bridge on a nodal line of that mode, then it wouldn't be good for the sound of the instrument, but it would be good for reducing the amplitude.
Well,
Yeah, changing anything changes everything.
Yeah, Jim, because you know, one of the standard explanations as to why cellos suffer, you know, from wolf notes more than violins is that the height of the bridge versus the width, you know, for cello bridges is much higher than violin bridges. You know, that's the explanation that you see.
I quite like Shellings' explanation, really. I think if you just, but the height of the bridge is part of it. Yeah, it's the strength to body impedance ratio, but it's true the higher bridge is one of the ingredients, but the undersized body, you know, the comparing the traditional cello with the Hutchins scaled instrument, which is 30% bigger or something, and most people can't wrap their way around, but sounds great, but isn't a cello. It's just different. And that allows you, by having bigger plates, you can get the resonances in the same place without going so thin. And then you make the impedance match to the strings more like a violin. But it's true that the height of the bridge, I'd say, is a factor, but not the main factor. The scaling argument is still the thing that wins.
Phew. Well, that was a pretty intense session on wolf notes. So thank you very much, Jim. Let's give him a great round of applause here.